In the realm of software development, the importance of rigorous testing cannot be overstated. A single flaw can have catastrophic consequences. One such instance is the ill-fated launch of the Ariane 5 rocket in 1996. A software bug led to the rocket's self-destruction just seconds after liftoff. The Ariane 5's tragic demise serves as a stark reminder of the critical role that integration testing plays in ensuring software quality. Integration testing seeks to uncover defects that arise from the interaction between modules, defects that unit testing alone cannot detect. Through real-world examples and insights into best practices, we aim to provide a comprehensive understanding of this crucial testing phase. By understanding the importance of integration testing and implementing it effectively, we can strive to prevent similar disasters and build reliable software systems. Integration testing is a critical phase in software testing that focuses on verifying the interaction between different software modules. Unlike unit testing, which tests individual components in isolation, integration testing aims to identify defects that arise when these components are combined. It ensures that data and control flow seamlessly between modules, that interfaces are properly defined and implemented, and that the overall system behaves as expected. Software systems are typically composed of multiple modules, each responsible for a specific functionality. These modules may be developed by different teams, using different programming languages, or even sourced from third-party vendors. Integration testing bridges this gap by providing a structured approach to verify the interaction between modules. It helps to identify defects early in the development cycle, reducing the cost and effort of fixing them later. By catching these defects early on, integration testing contributes significantly to the overall quality and reliability of the software system. It provides stakeholders with assurance that the system is a cohesive and functional whole. Integration testing encompasses various approaches, each with its strengths and weaknesses. Choosing the right approach depends on factors such as the system architecture, development methodology, and project constraints. Let's explore some of the most common types of integration testing. 1. Top-down integration testing. This approach starts by testing the top-level modules, progressively integrating and testing lower-level modules. Stubs, which are dummy modules that simulate the behavior of lower-level modules, are used in place of modules that are not yet developed or integrated. 2. Bottom-up integration testing. In contrast to top-down, this approach begins by testing the lowest-level modules first. Drivers, which are programs that invoke the modules being tested, are used to simulate the behavior of higher-level modules. 3. Big Bang integration testing. This approach involves integrating all modules at once and testing the entire system as a whole. 4. Incremental integration testing. This approach combines aspects of both top-down and bottom-up testing. Understanding the nuances of each approach helps teams choose the most effective strategy for their particular situation. Top-down integration testing follows a hierarchical approach, starting from the top-level modules and gradually moving down the system hierarchy. It simulates the flow of control from the user interface or main program module down to the lower-level modules responsible for data processing, business logic, and database interactions. The process begins by testing the top-level module, which typically represents the user interface or the main control module of the system. Since the lower-level modules may not yet be developed or integrated, stubs are used to simulate their behavior. As the testing progresses, lower-level modules are gradually integrated, replacing the stubs. This process continues until the entire system is integrated and tested. Top-down integration testing is particularly useful when the high-level modules are developed and integrated first, allowing for early testing of critical system functionalities. In this section, we'll explore bottom-up integration testing, building from the ground up. Unlike top-down integration testing, the bottom-up approach starts from the lowest level of the software architecture, gradually moving up the hierarchy. It focuses on testing the individual modules that form the foundation of the system, ensuring that they function correctly before integrating them with higher-level modules. The process begins by testing the lowest-level modules, which typically represent data access layers, utility functions, or other foundational components. Since these modules are not yet integrated with higher-level modules, drivers are used to simulate the behavior of the calling modules. As the testing progresses, higher-level modules are gradually integrated, replacing the drivers. Bottom-up integration testing is particularly beneficial when the lower-level modules are developed and integrated first, allowing for early detection and resolution of defects at the foundational level. Next, let's discuss Big Bang integration testing, the all-in-one approach. Big Bang integration testing involves integrating all modules of the software system at once and testing the entire system as a whole. This approach is often perceived as the simplest and fastest way to perform integration testing, as it eliminates the need for incremental integration and the creation of stubs or drivers. However, while Big Bang integration testing may seem appealing due to its apparent simplicity, it comes with significant drawbacks. One major disadvantage is the difficulty in isolating and identifying defects. When a defect is encountered during testing, it can be challenging to pinpoint the source of the problem, as all modules are integrated simultaneously. Due to these drawbacks, Big Bang integration testing is generally not recommended for large and complex software systems. Finally, let's consider incremental integration testing, a step-by-step approach. Incremental integration testing offers a more controlled and systematic approach compared to Big Bang integration testing. It involves integrating and testing modules in small increments, gradually building up the system, and verifying its functionality at each step. This approach allows for early defect detection and isolation, as each increment introduces a limited number of new interactions. There are two main strategies for incremental integration testing, top-down and bottom-up, as discussed earlier. Incremental integration testing offers several advantages over Big Bang integration testing. It allows for early defect detection, as defects are identified and resolved as soon as they are introduced. This reduces the risk of encountering multiple defects later in the integration process. Section 8. Tools and environments for integration testing, facilitating seamless integration. Integration testing often involves complex scenarios and vast amounts of data, making it essential to leverage tools and environments that streamline the process. Testing frameworks. These frameworks provide a structured environment for writing and executing integration tests. They offer features such as test runners, assertion libraries, and reporting mechanisms, simplifying the process of creating, running, and analyzing tests. Mocking frameworks. Mocking frameworks enable the creation of mock objects, which simulate the behavior of real objects. This is particularly useful in integration testing when interacting with external systems, databases, or modules that are not yet developed. Continuous integration, continuous delivery, CI/CD tools. CI/CD tools automate the process of building, testing, and deploying software. By leveraging these tools and technologies, teams can streamline their integration testing efforts, improve test coverage, and enhance the overall efficiency of the software development process. Section 9. Real-world examples, integration testing in action. The importance of integration testing is evident in countless real-world scenarios, where it has played a crucial role in preventing software failures and ensuring the smooth functioning of critical systems. Let's delve into some compelling examples that highlight the impact of integration testing. E-commerce platform integration. Imagine an e-commerce platform that integrates with various third-party services for payment processing, shipping, and inventory management. Integration testing ensures that these integrations function seamlessly, preventing issues such as failed transactions, incorrect shipping addresses, or inaccurate inventory levels. Financial systems integration. In the financial industry, where accuracy and reliability are paramount, integration testing is crucial for systems that handle transactions, manage accounts, and generate reports. Integration testing ensures that data is transferred accurately between systems, preventing financial discrepancies and ensuring regulatory compliance. Healthcare systems integration. Healthcare systems often involve the integration of electronic health records, EHRs, laboratory information systems, LIS, and other critical applications. By rigorously testing the integration points between different software modules, organizations can mitigate risks, improve software quality, and enhance customer satisfaction. Section 10. Defect management in integration testing. Addressing the flaws. Defect management is an integral part of the integration testing process. When defects are discovered during integration testing, it's crucial to have a systematic approach to address them effectively. Here's a typical defect management process in the context of integration testing. 1. Defect detection and reporting. As integration tests are executed, defects are identified. These defects are documented in a defect tracking system, including details such as the test case that revealed the defect, the system environment, and the steps to reproduce the issue. 2. Defect analysis and prioritization. Once defects are reported, they are analyzed to determine their severity and impact. High-priority defects that significantly affect functionality or data integrity are addressed first. 3. Defect assignment and resolution. Defects are assigned to developers for resolution. Effective defect management is essential for ensuring the quality and reliability of software systems. Section 11. Conclusion: Integration testing, the cornerstone of reliable software. In conclusion, integration testing stands as an indispensable pillar in the realm of software development, playing a pivotal role in ensuring the creation of dependable and robust software systems. As we have explored throughout this essay, integration testing goes beyond merely testing individual components in isolation. It meticulously examines the interactions between these components, uncovering potential issues that might arise from their integration. From the unfortunate incident of the Ariane 5 rocket to the seamless functioning of e-commerce platforms and the critical accuracy required in financial systems, real-world examples have vividly demonstrated the far-reaching impact of integration testing. By adopting a proactive approach to integration testing, organizations can mitigate risks, reduce development costs, and ultimately deliver software that meets the highest standards of quality and reliability. As software systems continue to grow in complexity, with intricate integrations becoming increasingly prevalent, the importance of integration testing will only continue to escalate. Embracing a comprehensive and well-defined integration testing strategy is not merely a choice, but a necessity for any organization striving to deliver exceptional software products. By investing in robust integration testing practices, organizations can pave the way for a future where software failures become a rarity and user satisfaction reaches new heights.